Here in section 4.4, we're going to be looking at what we call optimization problems. And part of working with optimization is looking for what we call the absolute extrema of a function. So we're looking for the absolute maximum value that a function will reach, and the absolute maximum values are the y values, and the absolute minimum values are also the y values. So the absolute maximum and minimum values. What we're essentially looking for is what is the highest point for the entire graph and what is the lowest point achieved on the entire graph. Remember, high and low are comparing y values. So look at my first graph. What is the absolute minimum or the smallest y value or the lowest point on the entire graph? So it looks like this point right here is the lowest point. So we would call this the absolute minimum. And it looks like it occurs when y is equal to 0. So y is equal to 0, the smallest point, or the lowest point, rather, on the entire graph. So this is the smallest y value. Do we have an absolute maximum? So when I go to the top, I see an arrow that tells me that the graph continues to increase and never stops to increase, and this side as well. So there is no absolute max. There is no highest point on this entire graph. Once I think I found the highest point, then the graph goes higher than that. So there is no absolute maximum. We call this graph an unbounded graph. In other words, if it has arrows, then it will continue to grow unbounded. So it says unbounded growth in one particular direction or another. So this is an unbounded graph. Okay, for the next graph, it looks like we have an absolute maximum value. The highest point on the entire graph looks like we achieve a y value of 4. So the highest point we will call the absolute max. So that's the absolute maximum point. It looks like, let's look down here. Do we have an absolute minimum? Do we have a smallest point that we could identify? And since we have these arrows that are pointing down, it's unbounded, which means it continues to go downward forever. So we don't actually have a lowest point. So in this case, we would say there is no absolute minimum. Okay, there's no smallest y value. All right, on this graph here, looks like we have an arrow going up and an arrow going down. So it's unbounded growth going up and unbounded growth going down. So there is no absolute max or minimum. So it has neither. Okay, we call these unbounded graphs, so unbounded regions. These graphs, if we have an unbounded region, the graphs are not guaranteed to have an absolute max or an absolute min. Now, does that mean that they never have an absolute max or an absolute minimum? And we've just identified that that is not the case. Sometimes they might have an absolute minimum, sometimes they might have an absolute maximum, but the key here is that we are not guaranteed to have an absolute max or an absolute min. So it could be that we have neither. What we want to look at in this section is what happens with a bounded region. So what if we have a function on what we call a closed interval, where we have a smallest x value and a largest x value, and the graph is completely contained within that region. So we have no arrows. Okay, we would call this a bounded graph. All right. If we have a bounded graph, then what we are guaranteed is that we will be able to find not only an absolute minimum, but we will also be able to find an absolute max. So we are going to be able to find both no matter what, if our graph is bounded. All right, so let's look at this first graph on the left. So on the left, if it's bounded, if it's a bounded graph, I won't have any arrows, and I will be able to completely contain the entire graph within a box. So here's my box. Now, what we're looking for then is what is the largest y value? Well, the largest y value would be, it looks like right here at the very top of the box, a y value of -2. This is the absolute max. So the absolute maximum value our graph achieves on this region is -2. And what we would say that this absolute max occurs when x is equal to -1. All right, what about an absolute minimum? So what's the smallest y value that we see on our graph? Well, the smallest y value would be right here at y equals -8. So y equals -8 we would call the absolute minimum value. And where does it occur? It occurs, looks like, we're just going to estimate here, it occurs when, looks like when x equals 1. Okay. What is the bounds? So this graph is on a closed interval, and when we look at closed intervals, we're talking about the x values that mark the very right and very left edges of our box. So that goes from -2 to 2. This is our bounded region. All right, let's look at our next graph here. Before we do that, let's just notice one extra thing here. Notice that the absolute max and absolute min occurred within the boundaries and did not occur at exactly x equals -2 or x equals 2. So these two happen to have occurred within the bounds and not on the edges. Well, when we look at this one, we put this graph in a box, and we can do that because there are no arrows. So we have a bounded region, or a closed interval, and that closed interval goes from x equals -4 all the way to x equals 2. Okay, what is the absolute max? Well, it looks like the absolute maximum value is 4. So that's the highest point on the entire graph. And the absolute minimum occurs at the very bottom there. It occurs y equals -12. So that is the absolute max and the absolute minimum. And let's look at what x value, what x values they occur. They occur when x equals 0. And when on here, when x is equal to -4. Oops, there we go. Okay, so the absolute max and minimum values are y values, the highest and lowest that the graph goes in terms of y, and they occur at the x values. Now notice that these two particular points that we found, one occurred within the bounds, and the other one occurred at the boundary point. All right, so what we want to consider when we're looking for absolute max and absolute min on a closed interval is not only the points within the region, but also the points on the boundaries. So depending upon where we cut the graph off, that could change an absolute max or an absolute minimum. So what we're going to be looking at in all of the examples we do on the next few pages is we're going to be looking for two things. We're going to be looking for those places on the graph that have those horizontal boundary lines. Horizontal tangent lines. Okay, where do those points occur? Well, they occur when the first derivative equals 0. And remember, when we were looking for relative maximum and relative minimum points, we were looking for horizontal tangent lines, or x values for which the first derivative equals 0. Now, are we guaranteed that if the first derivative equals 0, that will be the absolute max or absolute min? And the answer is no. But we're going to compare all of those relative maxes and all those relative mins and see which one is the absolute highest of all of those and the absolute lowest of all of those. All right, here on our second graph on the right, this particular point has a horizontal tangent line. And if I was to look at the first derivative, it would equal 0 at x equals 0. So that's a relative max. And then for this particular graph, it turned out to be also the absolute max. Now, where do we also have an absolute minimum? Well, right here we had an absolute minimum, but notice that at the bottom here, this does not have a horizontal tangent line. Okay, here's our tangent line, it's definitely sloping up. Why is that an absolute minimum? Well, because it occurs at the very edge of the graph, and the graph happened to be going down all the way down there, our graph got cut off right there, and so this happens to be the point on the boundary line, on the left boundary there, happens to be the lowest point on the entire graph. So some of our absolute max and absolute minimum points will occur at the boundary points, so we want to consider those as well for absolute max and absolute minimum. So essentially what we're doing is we're going to identify all the places on the graph that are relative maxes and relative minimums. Then we're going to compare the y values of all the relative maxes and all the relative minimums. And we want to know which one has the highest y value and which one has the lowest y value. So we're going to compare all those places on the graph that are considered relative maxes and mins, and we're looking for which one has the highest and lowest y value. The one that has the highest will be the absolute max. The one that has the lowest will be the absolute min. Alright, so we're going to look at a few examples where I'm going to give you a function in a closed interval, and I'm going to ask you to find the absolute extrema on that closed interval. So the first thing we're going to do is we're going to find the first derivative, and then we're going to look for what we call the critical numbers. These numbers are in the domain of f, so that means they're not x values that are asymptotes or holes. They're actually a point on the graph. And these are x values that have a first derivative that equals 0 or a first derivative that's undefined. Once we gather all these x values together, we want to plug them back into the function, and we're going to compare the y values of each of them. And whichever has the highest y value or the lowest y value, that's going to represent our absolute max and absolute min on that interval. So we're testing a few things. We're testing the boundary points. So you notice that the interval is given as a comma b. So we're going to test the x values on the boundary lines, and then we're also going to test those critical numbers, the places on the graph that have those horizontal tangent lines. And then we're going to compare all of those and then find our absolute max and absolute min. Now before we do that, what I want to do is kind of give it a mental picture of what we're accomplishing here. I have the function here and my interval, and I'm going to look in Desmos. We're going to look at that graphing calculator. Just going to pull that up. And here is our function. So here in blue, we have our function without any boundaries. So it has it's an unbounded graph. It goes up and continues to grow and go up forever. So this particular graph would have an absolute minimum, but would not have an absolute maximum. The absolute minimum, it looks like, would be about right there. It looks like about 7.6. Now, what happens if we actually cut this graph off at different locations? Will the absolute max and minimum ideas change? And the answer is yes. So let's hide this one and let's pull this one up. So this one is the original graph, but the boundary points, the boundary lines, the x values go from 0 to 5, so it's bounded. So I can actually zoom out, and I should be able to, at some point, visualize that entire graph. So it doesn't go up forever anymore, it doesn't go down forever. Okay, so we have bounds. So the very top point of our graph looks like it's going to be represented by 5, 64. So the absolute maximum would be 64 and occurs when x equals 5. And it looks like the absolute minimum is still what it was before. It's about 2/3, it looks like, and 7.6 for that y value. All right. Now, here's the question. What if I had to cut the graph off at a different location? Would that absolute minimum always be the absolute minimum? And the answer is no. So let's look at this graph here, and let's take the bounds and let's change it to be something else. Let's change the bound to 3. Let's say I'm only looking at the graph from x equals 3 to x equals 5. Now if I do that, I still see the whole graph, and this is still the absolute max, but now the absolute minimum would occur when x equals 3, and that absolute minimum value would be a y value of 24. So the boundary points here play a really big role in what the absolute minimum and maximum values will be. All right. So let's go back to the original bounds, and let's look here. Let's go back to the original graph first. If we were in the past section, what would we do? In the past section, if I wanted to find a relative max or a relative minimum, I would look for the places on the graph where they have the horizontal tangent line. So I'd find my first derivative, set it equal to 0, and this is the only point that I would come up with, is that point at the very bottom of the graph. And we didn't talk about absolute max and absolute min before, but that would have been the absolute max and the absolute, that would have been the absolute minimum value. All right, so it's a relative minimum, and also it would have been the absolute minimum. Now, when we look at the bounded graph, notice that that is still the place where we find that absolute minimum. Okay, it still has that horizontal tangent line. Okay, but the top half of my graph doesn't have a horizontal tangent line. Okay, so we're not going to always have a horizontal tangent line at the absolute max and absolute minimum values. So that's why we test the boundary points as well, to see what's happening there. So a big part of finding absolute maxes and mins is testing what are the y values at those boundary points. So the first thing that we're going to do is we're going to look for the places on the graph that have those horizontal tangent lines. So we're going to find the first derivative, and then we're going to set it equal to 0. So step 2, we're going to find those critical numbers by setting that equal to 0. We know it's not going to be undefined because it's a polynomial function. So we're going to solve for x, and I end up getting a critical number of x is equal to 2/3. So this is definitely in the domain of the original function because that has a domain of all real numbers. So we did this, we found our critical number. The next thing that we're going to do is we're going to plug in to our original function. Notice it's talking about the original function. That's what we're interested in, the y values of the original function. We're going to plug in f of 2/3. We're going to plug in 2/3 into the original function. We're also going to plug in the boundary point. So we're going to plug in 0 and we're going to plug in 5. Okay, we want to see what the y values of all of these points are. So let's plug in 0. That's pretty easy. If I plug in 0 into my original function in place of x, I get 9. If we plug in 5, we just throw this right into our calculator. I end up getting 64. We already looked at that and found that on our graph. And we want to know what happens if we plug in 2/3. So if we plug in 2/3, and I'm going to go ahead and work with the fractions. So I want an exact answer for my final answer. So I'm going to go ahead and work with the fractions to find out what that exact answer is. So that would give me 3 times 9, 4 9ths. Square the top, square the bottom, minus 8/3 plus 9. Let's simplify this part right here. I would get a 1 and a 3, so we ended up with 4/3 minus 8/3. We need a common denominator here as well, plus 27/3. That gives me 23/3. So this would be the exact value of that y value. Hard to tell exactly what that number is in comparison to the others, so we'll put that into our calculator so we can do the comparison. So I get 7.66. So we want to compare the y values and see which one is the highest. So here's the highest, so this represents the absolute max. And this one's the lowest and represents then the absolute minimum value of the graph. So I want to report the actual point here. So it occurs when x equals 2/3. And I'm going to give the exact value here without any rounding. I'm going to give the y value as 23/3. And then the absolute max occurs when x equals 5. So we'll say 5, 64 represents the point that is on the graph as the highest point on the graph. All right, here we want to find the absolute max and absolute minimums. So the first thing we're going to do is we're going to find the first derivative. So we're going to use our power rule. That gives us 1 to the negative 2/3, or 1 times x to the negative 2/3 power. Let's go ahead and bring that down to the bottom of the fraction so we can make it a positive exponent. So we're looking for two things with our critical numbers. We're looking for where the first derivative is 0 and where the first derivative is undefined. So if we set it equal to 0, we're going to run into a problem because when I cross multiply 0 times x just gives me 0, 1 times 1 gives me 1, and there is no solution there. So no x value comes from that. What about where the first derivative would be 0? Well, we do have a variable in the denominator, and so that variable would be 0 if we said x was 0. So if x was 0, x to any power would make our denominator 0. So keep in mind that this is different than what we did in the last section, because what we're doing is we're taking these numbers and we're putting them into the original function to compare all of the y values. So we're going to, for our third step here, so first step is finding the first derivative, second is finding those critical numbers. For our third step, when our optimization problems here, is we're going to plug those into the original function along with the boundary points. We're going to plug in negative 27 and also negative 8. Now before we do this, let's go back to our interval. So this is really important, our bounded interval. Is 0 within that interval? And actually, if we think about it, 0 is somewhere over here, right? It's larger than all of those negative numbers. So it's not within the interval in consideration. So I'm going to go ahead and cross this one out, and I'm going to say 0, x equals 0, is not in the boundary interval. So we're not going to consider that. So we're just going to consider for this particular problem the boundary points. So I'm going to plug in negative 27. Now remember, we're plugging it into the original function to compare the y values of those points. So it's 3 times, and remember that raising something to the 1/3 power is the same thing as taking the cube root of it. So the cube root of negative 27 would be negative 3. 3 times negative 3 is negative 9. 3 times the cube root of negative 8. Cube root of negative 8 is negative 2. So we end up getting negative 6. So which one of these is the highest? This one is the highest y value, and this one has the lowest y value. So this is our absolute minimum value on the graph, and this is the absolute maximum value on our graph. All right, so we want to be careful about our interval that we're given. So here we have f of x equals negative x squared plus 10x plus 5, and we can already imagine that this is an upside down parabola. Okay, you might think that is the absolute maximum, but keep in mind that it depends upon where the interval cuts the graph off. So let's find the first derivative. Gives me negative 2x plus 10. We're going to set the first derivative equal to 0. This time it's not possible for the first derivative to be undefined, so we're not going to worry about that. So we have negative 2x plus 10 equals 0. That's negative 2x equals negative 10. Dividing both sides by negative 2, we get x equals 5. Now, is x equal 5 within the boundary? That's the first thing that I would ask myself before I did anything. And the answer is no, it's not there. So we're not going to consider this value. Okay, so we are only going to consider the boundary points again. So we're going to compare the y values of x equals 7 and x equals 10. So when we plug in a 7, we have negative 7 squared plus 10 times 7 plus 5. We're going to throw that in our calculator, being careful not to square the negative here. That's out front. Alright, so I get 26 for that. If you're doing it by hand, you want to keep in mind that the 7 is the only thing that's being squared, so this would be negative 49 plus 70 plus 5, and that should give you 26. When we plug in the 10, we get negative 10 squared plus 10 times 10 plus 5. Throw that in your calculator, being careful not to square the 10. And if you're doing it by hand, you should get negative 100 plus 100 plus 5, so we end up getting 5. So this becomes the absolute maximum value, and this is the absolute minimum value for this particular interval. So let's put this one in Desmos as well, just to get a visual of why this point right here at the vertex where we had our first derivative equals 0, why that wasn't in consideration for an absolute max and absolute minimum, because it looks like it would be the absolute maximum of our graph. So let's look at plugging this into Desmos. Alright, so when we look in Desmos, we would see that if I have the graph without the boundaries, that this would definitely be the absolute maximum value of our graph. It would be 30 when x was equal to 5. Okay, but notice that our boundaries, when we include the boundaries, that we don't get the entire graph, we get just a portion of it. So we only get this portion on the side, we actually don't get that point that's at the top. So we actually only get a portion of the graph, and it's only that right side. So we don't get that point that's at the very top of the original graph. So our absolute maximum, 726, so our absolute maximum value is 26 and occurs when x equals 7, and the absolute minimum was a y value of 5 when x was equal to 10. Alright, so in this example we're going to do the same thing. We have our closed bounds. We're going to find the first derivative. Okay, so this is our quotient rule. It's the denominator times the derivative of the numerator, which is 1, minus the numerator times the derivative of the denominator all over that denominator squared. Since I'm going to use this, I am going to simplify. So I get x squared plus 1 minus 2x squared. And then we're going to add like terms at the top, so I get negative x squared plus 1 all over x squared plus 1 squared. So remember, doing two things. we're going to set the first derivative equal to 0, and we're going to look for where that first derivative is undefined. All right. So let's do the first part here. Let's take that first derivative, set it equal to 0. So that means we're going to cross multiply. So 0 times that gives me 0, 1 times that gives me that. Okay, that's pretty nice. Pretty simple. Now we're going to bring the x squared over to the left side. It becomes a positive x squared. And then we're going to take the square root of both sides. And we want to make sure that we include both plus and minus 1 when we take that square root. Okay, is our first derivative ever undefined? Do we get more points from that? And the question would be, does that denominator ever equal 0? Is there an x value that would cause that to happen? So we'll take the square root of both sides, try to solve for x, subtract the 1, and we run into a problem because x squared, if I square something, I never get something negative. So for this particular example, then there would be no solution. Okay. Now keep in mind that if you did try to take the square root of both sides at this point, then you would get square root of a negative number, which we said at the beginning of the semester was imaginary. So we're not going to get any points from finding out where the first derivative is undefined. So now we're going to compare the values that we get. So we're going to plug into the function. Remember, we're plugging into the original function. Let's scoot up a little bit. We're going to plug into the original function the critical numbers that we found. We're working with h. So we'll put in 1 and we'll put in minus 1. But we're also going to put in the boundary point, so we don't want to forget that. So we're going to plug in negative 2 and we're going to plug in positive 2. See what happens. So you plug in a 1. Remember, we're plugging into the original function because we want to know the y values of the points on the original graph. So we'll plug in a 1 in place of x. We end up getting out 1/2. If I plug in a negative 1 in place of x, we end up getting out a negative 1/2. So we're going to plug in a negative 2 in place of x. Okay, we end up getting negative 2/5. Plug in a positive 2 in place of x, and we end up getting out a positive 2/5. So what is the absolute maximum value here? So the largest value that we see would actually turn out to be 1/2. So if you couldn't tell that from the fractions, you could always put this into your calculator and find the decimal values of them, if that would help. If you put 2/5, you get negative 0.4, and so this turns out to be a positive 0.4. So 0.5 is the largest of all of these, so this turns out to be the absolute maximum value of this region of our graph. And the smallest value actually turns out to be negative 0.5. So this turns out to be the absolute minimum value of our graph. Okay, we're going to look at a couple of word problems here. So one of the reasons why we might want to look into optimization is to find out maybe how to solve some real-life examples. So for example, here we have an apartment complex that has 100 two-bedroom units that they can rent. The monthly profit in dollars from renting out X number of apartments is given by this function here. So we have our profit function. So what we want to do is we want to find what is the absolute maximum profit that we can make. So we want to optimize the situation. We want to maximize the profit. We want to know how many units we should rent out in order to maximize the profit. And then we want to know what is that maximum profit that we can get. All right, so let's see what it's going to be. First of all, we have a function, but it doesn't look like it has any boundaries. What are the bounds? Well, we can't rent out a negative number of apartments. We can rent out 0. So 0 would be the smallest number of apartments that we could rent out. The maximum number of apartments we could rent out would be 100. So while it may seem that we don't have bounds, we actually do have some real-life bounds and some logical bounds about what x can actually be. So we want to find out what is the maximum profit, or what is the largest value of p, or y, if you will, on this particular bound, so on this closed interval. So we're going to do the same thing we did a few minutes ago. We're going to find the first derivative. Okay, we're going to set that equal to 0. and then we're going to solve for x. So I'm going to subtract over the 1760, divide both sides by -20, and I get x is equal to 88. Now, would we get more profit for renting out 88 apartments or maybe 100 apartments? What if we rent out all 100? So that's what we want to know. So we're going to plug everything into our original profit function. We're going to plug in 88, the critical number that we found in the last step. We're going to plug in 100. And I think we know the answer to plugging in the left bound of 0. We know what we're going to get for that. That's definitely not going to be our maximum profit renting out 0 apartments. And we can tell right away if we plug in 0, these first two terms are going to cancel out or go away, and we're going to be left with -50,000. Okay, so that's definitely not our maximum profit. And we can tell it makes sense that if we rent out 0 apartments, we're still paying money to own those apartments, so we would actually lose $50,000. So let's see, it's kind of a race now between 88 apartments and renting out all 100 apartments. So we're going to plug this into the original function and see what we get. So it looks like I get $27,440 of profit for the month. So if we plug in 100, what do we get? Okay, and I got, let's see, $26,000. Alright, so if we rent out all 100 apartments, we only get $26,000 in profit. So if we rent out 88 apartments, it looks like that would be our optimal solution here would be to rent out 88 apartments so we can make a maximum profit of $27,440.